Okay, it's officially recording now. I guess it's a sign that the course is resuming. I hope you all had a nice break, lunch, dinner, or like a snack at like 4 a.m. if you're in Australia.
I'll be honest, I actually laid down and I fell asleep. I'm glad I set my alarm.
Power naps are the best.
Yeah, power nap.
Cool. Okay,
I
so
plan to
let's
have my power nap now. I was kidding.
All right, so let me share the screen again. Here we go. So maybe you can take a few minutes to gather some questions. We've covered quite a lot of material so far. Are there any questions?
Julian, I just have a question regarding the 7T template, which I just found out about a few weeks ago. If we have our 7T data, how should we go about using new templates, which might just be available, but maybe not thoroughly tested? Should we try to use the current templates that are available and then maybe try to load the 7T templates and try them and compare? Or how do we even approach, something like that?
Right. Yeah, I know this is it's a very important question. So the problem with the existing the recent templates that have been proposed, the pediatric one, 71, also the microstructure templates that Tanguy Duval was developing based on electron microscopy segmentation. They don't have all the features that the PAM50 has. Specifically, it does not have the white matter atlas attached with it. So you could register to a template. You could register to the 70 templates, but then what do you do with it? Right? If you want to extract DTI, in the cortical spinal tract, you need a white matter atlas to it. So what we need to do is warp the current white matter atlas to these new templates, and then the full pipeline will be accessible. Yeah.
Okay, thank you.
I had a question about something on your slides, number 46. In the notes, it says that SCT can accommodate labels all the way down to L2. How can we label levels below that? If we have, for example, an image of a pediatric spinal cord and we have the entire spine, or all the levels.
Right, like for example, L5, right?
Right, yeah.
Okay. So the reason it says that SCT can accommodate levels down to L2 is because the PAM50 has levels down to L2. So if you're not using the PAM50, if you're doing something else, then you can use other, you can use additional labels. For example, if you want to compute cross-sectional area between L2 and L5, then you don't need the PAM50 to do that, and you can basically do it with SCT. It's fine. Right? So this sentence, accommodate down to L2, is specifically with the PAM50 in mind.
Okay. And do you know if the pediatric template that is in the works will also go down to L2, or will it be different than PAM50 in that respect?
So we don't have a clear strategy. If there are requests to go, to include more levels, we will include more levels. But basically, the SCT is designed for users, and users are, in this call right now. It's all of you. So if we don't have the requests, we won't make it happen. So in order to make the requests, you need to let us know what you need, maybe on the forum, and then we will add it to our to-do list. And in fact, if you need the label like right now, it really takes only, like, you could edit the PAM50 yourself. I don't recommend doing that, but at the end of the day, it's only a single voxel that is that corresponds to these labels. So you could edit the PAM50, add the labels that correspond to L3, L4, and then Sct will work with those additional labels. All right. So I think we can close this. Close that. So let's go back to our slides. Okay, so we did our registration. We played with some parameters. We realized that tuning the parameters differently would produce different results. So we came back with the original default one. And now we want to go a little more into the details of what are the different flags that are specific to register to template. So if we open our terminal at Sct register to template, maybe Sandrine, if you could add a note on the fact that we don't need all this big path here, so I should update my terminal in the future, because it's taking a lot of space. So Sct register . Okay, so we have a flag called ref, as you can see here. So the possible values are template or subject. By default, it is template. What does that mean? What it means is that the destination image used for the registration will either be the template or the subject. By default, it will take the MRI that you put in, MRI from your patient, and it will register it to the template. You can do it the other way around. You can take the template and register it to your subject, right? There are subtle differences. One difference is that when you select ref templates, the chord will be straightened. Whereas if you use ref subject, the chord will not be straightened. Okay. So next natural question is, when would you like to use ref subject? Meaning, when would you like to not straighten the spinal cord? And for example, if your image is acquired axially with high anisotropic resolution, so you have like very thick slices and high in plane resolution, the straightening process that you saw before, you remember you have your curved spinal cord that will be straightened. That algorithm will produce through plane interpolation errors, and you don't want that. So in this case, it is better to register the template to the subject in order to avoid those inaccuracies that are related to this straightening procedure. Obviously, if you do that, and you have like axial images of the spinal cord, you want, and that really comes back to the acquisition of the images. You want your acquisition in such a way that the slices are quasi-perpendicular to the spinal cord, right? So it's very important that when you prescribe your acquisition and your slices, you try to have the slices as orthogonal as possible in order to reduce those the partial volume effect that could happen if you have like a tilted field of view. Okay. Ken, yeah, I see you have a question.
Yeah. So based on this, would you not, I guess, if you acquire axial data that's anisotropic, how would you recommend doing voxel-wise analyses on those data sets? Or do you recommend not doing that? Like if you want to warp the subject level data to a template. Yeah.
That's a great question. Excellent. Okay. So when you use ref subject or ref template, you still have two warping fields that are output. You still have a forward warping field and a backward warping field, right? So you can always take your axial images and put them into the template space. You can still do that, right? The only difference is that there won't be any straightening warping field calculated. Does that make sense?
Yeah, thank you.
And try that. You see that it actually works okay. Yes, Pedro?
So just to understand a little bit the nature of this transformation. So when you do so is this transformation somehow symmetric? Like, I mean, is it invertible in a way that if you switch template and subject, or if you invert the transformation, you're going to get the same results?
Yeah, that's a great question.
And related to that question, are these transformations diffeomorphic? So are they?
They are diffeomorphic. Exactly. Okay. So that answers your question. The fact that the forward and the inverse warping fields are diffeomorphic, and so if you apply the forward to A, you get B, and if you add if you then apply the backward to B, you get A.
You get A. But the nature. But the transformation is going to be slightly different if you put the template as the destination or the subject because of the probably the cost function you're trying to optimize, and somehow you don't get exactly the same results for numerical reasons.
That is correct. You don't get the exact same results because the transformation will be estimated in a space that is different, that has like a different metric size, resolution, contrast, and so on. Yeah.
Okay, thank you.
So I really invite you to try both, and it helps understanding the subtleties behind those flags and the ways we can register the data. But the main rationale and the motivation for choosing one parameter versus the other is really explained here. Ken, do you have another question or?
Yeah. So I guess. Usually we always use a T2 for this. So for that, it's a high resolution T2. So that's okay then. But then when we register functional data to the template, we use SCT register multimodal.
So another good question. The SCT register multimodal does not include a straightening. Okay. The straightening is only included in the register to template. If the flag ref template is used. Yeah. And so, if we want to go back to the slide 62, we're going to go back to this one. What you just described, Ken, in fact, is the register to template with the ref template flag would be this thing, right? Once you do this, you have a warping field, and then you can use this warping field as an initial step for your metric, like fMRI, DTI, whatever. And then you do register multimodal. And in this case, the DTI or whatever and the anatomical T2 are already fairly close by, right? Because they have been acquired with the same participants, similar positioning. So there is only some like finer registration that needs to be done. These are done with register multimodal, and then the warping fields are concatenated between the T2 to template and metric to T2. Right? Okay. So we've already covered that, the flag param that lets you choose between different acquisition, different registration parameters. So as we talked about before, what we did so far was to register the template using two labels at the mid-vertebral levels, right? So C3 and T2. But if your volume spans a large superior-inferior length, for example, C2 to L1, then this linear scaling that we discussed before might not be like accurate anymore, right? So if you want to really have like a good vertebral-based estimation of your metric, you might want to, label all your disks and use those disks to do the registration. And so you can do it with this command. Instead of inputting -L, you would input -L disk. And in that case, you would use the labeled disk as opposed to the labeled vertebra. Okay. Conversely, if you have a very small field of view, so you're dealing with, like, for example, myelin water fraction that were acquired in a single slice, right? If you have a single slice and this slice is centered at C3, C4, then you cannot have more than one label, right? Because you only have one slice. So in that case, you can use a single label that is, for example, 4, if your single slice is centered at C3, C4, and you can use that single label for the registration to the template, right? So in that case, there would not be this affine transformation. It will be skipped, right? Because we only have one label, and the disk will simply be the disk from your participants. Let's say if it's C3, C4, there will just be a translation that would bring this C3, C4 disk to the C3, C4 disk of the PAM50 template. So it will be a translation as opposed to an affine transformation. Okay. Question that I often get also is that, so we played with some parameters and we saw that the parameters have an impact in the registration results. So if you have images with highly compressed spinal cords, which often happens in degenerative cervical myelopathy, spinal cord injury, then you can use custom parameters. So in this case, we use the column-wise algorithm because it offers a lot of degrees of freedom in the way the cord can be deformed in order to match that of the template. Okay. So again, I invite you to play with those parameters, and if you have any questions or need for clarification of what exactly those algorithms do, feel free to reach out. So once the transformation is estimated, you can apply it to bring the template into the subject's native space. And so by default, the function Sct warp template is used here, and it will select the PAM50 template, which is located under the Sct like Spinal Cord Toolbox directory, and then warp it to your subject space. So that's what we're going to do now. I'm in the T2 folder. These are all my files. I have my T2 image here, my segmentation. And importantly, I have the warping field that brings the anatomical image to the template and the one that brings the template to the anatomical image. So that's the one we want to use now, right? We're going to do Sct warp template. Minus D is the destination image. It's going to be the T2. Minus W is the warping field we're going to use. So warp template to anat. Minus A is if we want to also warp the white matter atlas. In this case, we don't need it. So I'm just going to say minus A0. And as before, we're going to ask for generating the QC report. So what it does is it uses Ant's applied transform to apply the warping field to the T1 weighted image of the PAN50, to the T2, T2 star, the spinal cord, the white matter, gray matter, CSF, and so on. Okay. And once this is done, we can run the facialized code to look at the image, or you can use your other favorite viewer. So I'm copying this thing, pasting it. And now this is, so we have a lot of images here. So I'm going to remove this, so we can look at it together. That's the native T2 image. And if I switch this one on, that's the registered PAN50 T2 template. Okay, so that's the template registered to your data. And we can also add the gray matter atlas. T2, so that's the gray matter. Again, it's only warped from the probabilistic template, right? We have not segmented the gray matter here because we don't see it on this contrast. And we can do the same with the white matter. Okay. We can also look at our QC report. You see there is a new line here that shows the warped white matter atlas on our image. Okay. So with a quick look, it seems fine, and then you can move forward with your analysis. So next thing we want to do now is finally get some results, some quantitative results. And the first one we're going to get is the cross-sectional area of the spinal cord that we want to average between C3 and C4 levels. Okay. So in order to do that, we're going to use a function called Sct Process Segmentation. So I'm opening my terminal. Sct Process Segmentation. The input will be the segmentation. Okay, we're going to compute the cross-sectional area based on the segmentation. I want to do this at specific vertebral levels, C3 to C4. For that, I'm going to use a vertebral level file. So I'm doing the flag vert file, which is under label /template /PAN50 labels. So these are the vertebral levels that have been warped into my subject space. And the output will be CSA, C3, C4, CSV. Okay, so it's done, and you can see that the output gives you a command that you can open, that you can copy paste, so that it will open it on your computer. If you're on Linux, it will say again like the appropriate command. I'm opening this. And on my laptop, the default for CSV file is the software numbers, which is on macOS CSV file viewer. So it shows, you know, a timestamp. So it's basically the when I did run this command, the version of SCT, which is useful if you want to, you know, get a track record of the SCT version that you've used for your analysis. The file name that this has been run on. The slices that correspond to the vertebral level you asked for. In this case, C3 to C4. This corresponds to slices 144 to 187. Okay. And finally, that's what you're after. It's the mean CSA that is averaged between these levels. Okay. And it's in millimeter square. That's the standard deviation. And we're going to talk about these other values a bit later. Actually, we can talk about this now. So the way the cross-sectional area is measured is by looking at the angle between the actual slice, okay, and the spinal cord center line. Okay? If the spinal cord center line is completely orthogonal, then the cross-sectional area will be the computed area on this slice. Right? But if the spinal cord center line has an angle with the slice, then the appearance, the projection of the slice will be an ellipse, right? Will be like a larger ellipse. So we need to correct for that. The way we correct for that is with the cosine of the angle between the slice and the center line. So that's the measure that is reported here. And you have two angles, one in the AP directions and one about the AP direction and one about the right-left direction. Okay. So these are the values that we're seeing here. Any questions so far?
Just a comment. So
yes.
The first time I run that the previous command to wrap the template, I think it didn't work as I was following along because it was using the register to template that we created, changing the defaults. So it looked really bad. So I had to rerun the register to template using the defaults for it to work. So I'm not sure if anybody else was confused at that step as well.
Yeah, that's a good comment indeed. Yeah, if you played with some parameters of the registration to templates, you might have like a wrong warping field. So make sure that you have the correct one. Yeah.
Julian?
Yeah.
How does that algorithm handle like the edge slices where it might only have half of a slice as you showed previously? Does it discard those, or does it include those into the calculation of the mean? Or can you use the median, to make it a little bit more robust to those edge slices?
Right. It will actually include anything that has a segmentation. So in case on the edge, if we have like a partial segmentation,
yes,
it will show you like a value that is abnormal, right? So there are various ways you can deal with that. The median will still be biased. It will be less biased by the mean, but it will still be biased. My suggestion would be to basically QC whatever, QC and make sure that whatever is important for you is accounted for. I know that these edge slices are not important for me because I want to compute between the C3 and C4. So I'm not worried about that. But if I had some like weird, segmentations around these levels, then I would be worried and I would look back at my segmentation. Yeah.
Okay, thank you.
Luis, do you have any other question? Oh, okay. Okay, so what if you want to aggregate cross-sectional area per level and not across level? In that case, you would use this flag per level 1, and it will give you the value of the CSA for each vertebral level. So let's try that together. So I'm putting the up arrow so that I have the same command as before that I can rewrite. So what I'm doing here is, so that's the same. And I'm calling it per level. And I need to add the flag per level 1. Okay, now I can open this one. And I have this new file now that has 2 rows. One row corresponds to vertebral level 4 and the other one to 3. And then I have the mean CSA for each of these vertebral levels. Okay. So now you would like, instead of specifying the vertebral levels, in some cases you might not have the vertebral levels and you're interested in specifying with the slice numbers, you can do it with a flag Z. Okay. So Sct Process Segmentation -I segmentation -Z for the slice 30 to 35 per slice, because I want the value, CSA value for each slice. And I'm going to call this file CSA underscore per slice. Okay, I have a bug because I use the wrong syntax. I should use 2 points like this. It's a good example of when you have a bug, your computer will not explode. Usually it says something that should be interpretable. In this case, I can see that there is a value error, which means that I had like the syntax was wrong. And I quickly recognize what was wrong just because I'm used to this software. But you know, if you have an error and you can't figure this out, feel free to email us or post in the forum. We are here to help. Normally this one should work. And then you can open it. And now I have slice 30, 31, 32, and so on, and the CSA value for each of these slices. Okay. Any questions so far? I see there is 7 questions here. Is this the default vert file? So yeah, actually, we don't need to specify a vert file. If I do this, oh, I did not specify a vert file, right? So you notice that in this command here, oh yeah, that's because I did not have any vertebral level. That's right. In this command, I did not use, I used vert file, but I could actually, I could remove this and it should work, I think. My memory is correct. Yeah, still works. Why? Because by default, the flag vert file will point to, by default, vert file will point to label template 150 labels. Okay. So you don't need to input this one because it's already by default. Okay. Any questions so far? Okay. So now we're gonna present a new feature that was not there in the last year's course. And you all know that when we compute the spinal cord cross-sectional area, we do this with respect to the vertebral levels, right? And so what we discussed in the past is that the relationship between the spinal cords, spinal levels, and the vertebral levels might not correspond well and might vary across individuals, depending on the age, depending on the ethnic origin, and in some cases you might want to use a referential system that is based on the central nervous system, right? And so that is what we're doing here. We are using the pontomedullary junction, which is shown here, and compute cross-sectional area based on the distance from this pontomedullary junction. Okay. Luis, yes, I see you have a question.
Yeah. So just going back one slice, I'm sorry to do this.
Mm-hmm.
So we compute the area per label and then per slice. Is there a way to correlate the slices to a label or the vertebral level? So how many of these 30 to 35 slices belong to a particular vertebral level? Is that?
Right. So, okay, you would like to know, yeah, I'm not sure I understand, sorry.
So on the first table, we have a mean of the area per vertebral level, right?
Yeah.
And on the second table, we have the means of the area at each particular slice.
Right.
Let's say I want to find out a little more granular in vertebral level 4, for example, all the slices that belong to that vertebral level.
Right. So I think, so you would do a per slice. I'll do a per level. And then let's call it per slice vert. Okay, so in that case, what you have is the slice number and the associated vertebral level. Is that what you were asking for?
Thank you. Yes, that's exactly what I was.
Great. So that's the command. I copy it in the chat. Okay. So coming back to the pontomedullary junction based approach, that's a project that Sandrine is currently working on, and maybe Sandrine, you can add the link to your current preprints, because there's a study comparing the PMG based method versus the vertebral level based method to compute CSA and what's the variability across individuals. So I'm going to show you how we do this. So the first step is to detect the PMJ. So for that, there is a function called detect PMJ that we're going to run. Detect PMJ. We have to input the T2 image for that. Say that it's a T2 contrast. And we're going to ask for the QC report. QC single subject. Let's look at the QC report. Refresh, detect PMJ, and the cross is right there where it needs to be. So we're happy with that. Next step is to compute the process segmentation, this time with a new flag called PMJ. So here, Sct process segmentation minus I T2 seg minus PMJ T2 PMJ. So that's the outputs that I just got. And I'm saying that I want to compute the cross-sectional area at a distance from a PMJ of 64 millimeter. And what's the spatial spanning of this of the CSA measurements? That's defined by the flag PMJ extent. So we're gonna center our window at 64 millimeter distance from the PMJ, and this window will be 30 millimeter large. Okay. And the outputs will be called CSA, PMJ, CSV. And we can also have a nice QC of that. QC single subject.
You missed an argument.
I missed an
For the
argument.
QC.
I did. QC image. It's nice when the error actually tells you what's the problem. Okay, so now we can look at the QC report. We have a new field here, and it shows the spinal cord center line and the distance from the PMJ. So we basically computed CSA at 60 millimeter distance from here, and the spanning window is 30 millimeter. So from there to there. Then we average the value in this window. Okay. So if we open the CSV file, it will look like this. So that's my cross-sectional area averaged within this this red window. Okay. Luis, yes?
Could you report slices within that window?
Yeah, actually, I've never tried it, but can we? Let's try. Can we do a per slice? It will be a world first.
Pretty sure it's an issue right now to
Yeah,
add the per slice.
let's see. It doesn't crash, but now let's see what we get. Wow, it works, amazing. Okay, cool. Well, so here we go. Okay. So we've talked about cross-sectional area, but in some cases, you might also want to output shape analysis, such as the ellipticity of the chord, the anterior-posterior diameter, the right-left diameter. And these are of particular interest for studying chord compression. For example, if you want to detect automatically highly compressed chord, then you might want to look for the anterior-posterior diameter, for example. So there's an article by Alan Martin in participants with degenerative cervical myelopathy, where he showed the benefits of using those more complex matrix shape. Yes, Lisa, you have a question?
Yes, just wondering, is this PMJ command line for the newest version of Spinal Cord Toolbox only? Because okay, that makes sense why it doesn't work for me.
Right, I should have mentioned that. It's working as of 5.4 version. Maybe Sandrine, we want to make a note in this slide somewhere that, or like in the slide note, that this is a feature as of 5.4. Yes, good point. Okay. Other questions for the process segmentation? Okay. So far, we've seen how to use PAM50 to quantify the morphometry of the chord on anatomical image. And now we'll see how we can use template registration for computing quantitative MRI metrics. So let's say you acquire other scans during the same session, such as DTI, MT, myelin fraction, fMRI. So the key here is to register the PAM50 template to those additional scans. Okay, so we'll see how we do this. Like for the anatomical T2 image, the first step is to obtain a proper segmentation of the chord. And here we're using an MT weighted scan. Okay, so that's it's showing an axial view of the MT weighted scan. So we're first gonna go to the MT folder, CD MT. I'm doing an LS to see what's in there. I have two images, and one with the MT pulse off and one with the MT pulse on. Okay. So now we're gonna segment the chord with deep seg. C minus I will be the MT1. Contrast is T2, okay, because we have a bright CSF and a dark chord. And QC report. Now it's going to be a bit faster because we only have, I think, 20 or 30 slices. So let's look at the QC report. Refresh. That's the output segmentation. Looks fine. As you can see, there is some missing segmentation here, right? So if you're really interested in like those and slices, you might want to manually correct for them. Right? But for the sake of this of the time that we have, we're gonna just accept this this segmentation. Next step is we want to create a mask, and this mask will subsequently be used to obtain a better registration results between the MT1 and MT0. Okay, and the reason it's going to get better results, that's something we talked about during Rob's talk yesterday when we were talking about fMRI registration, is ultimately the only thing you care about is the spinal cord and not the rest of the tissue, right? You don't care about the muscles, you don't care about the fat here. So if you input the entire image in the registration algorithm, the registration algorithm will look at all the pixels and it will try to find the best combination of parameters to match all the pixels in the tissue. It's slow and it's sub-efficient. So what you really want is to tell the registration algorithm to only register the part that is inside this mask. Okay, so that's why we are creating a mask here. Okay, and the way we do that is automatically, because we already have the segmentation. So we can say create a mask around the segmentation. Okay, so that's what we're going to do now. Sct create mask. The inputs will be the image we want to create the mask on. And we have different methods to create the mask. In this case, we're going to use the center line. And we input the segmentation that we just created from the MT1. The size of my mask will be a cylinder of 35 millimeter diameter. it's going to look like a cylinder. You can use also a box or a Gaussian kernel. And here we want a cylinder. And I'm going to call this mask MT1 and the extension. Okay, let's look at it. Okay, so you see in red, you can put it in yellow. It's the mask that I just created. Okay. Now that we have this mask, we can register the PAM50 to the empty space. And note that we don't use the function Sct register to template to do that, but instead we will use Sct register multimodal. And the reason being that we start from the pre-registration, the registration that we did before between the PAM50 and the T2 weighted scan, which already contains information about vertebral labeling and a pre-registration, right? So I'm gonna copy this, or I can just type it. It's fine. So Sct register multimodal. My input image will be the PAM50 template. So I can point to sctdir /data PAM50 template PAM50 T2. So that's my input image. I also specify the segmentation, input segmentation, so iseg. And that's going to be the segmentation on the PAM50 template. So data PAM50 template PAM50 chord. And the destination image is the MT1 scan. I also need to specify a destination for the segmentation. I forgot the dash here. MT1 seg, which we just obtained. The mask that we created, which is mask MT1. We need to specify the initial warping field that brings the PAM50 to the T2 weighted scan that we computed before. So ... to go to the parent directory, T2 to go to the T2 folder, and then warp template to ANAT. Okay. And we're also gonna specify custom parameters here. For the first step, we want to use the segmentation, and we're gonna use the algo center mass. And for the step 2, we're going to use segmentation again. The algo will be B-spline sin. We want this to be slice-wise with 3 iterations. Output warping field will be called warp template to MT. And I want my QC report. Single. So that's a long syntax. Now it does a slice by slice registration for step number 2. Okay, let's look at our QC report. Refresh, register multimodal is here. And now we can compare we can assess the segmentation between the MT scan and the PAM50 template. Okay. So even though the segmentation, as you remember, was a bit problematic here, I'm putting back the segmentation. You see there is some part missing here. The registration is quite forgiving. See? still, it's not completely perfect, but it's still, my view, acceptable. Let's say if you want to quantify metrics across high number of slices. Luis, I see you raising your hand. Yeah.
Yeah, I was just wondering if you can speak a little bit about the rationale behind changing the type in the two steps.
Right. So while I'm explaining this, we can actually run it without changing the steps so that we can figure out what's the result without it. So I'm gonna put it default. Right. So the default parameters, you can see them here. For step 1, it's using the image. In general, when I have the segmentation and when I trust the segmentation, I don't like very much to use the, oh no, sorry. Yeah, right. I don't like to use the image because the image can be hampered by artifacts, right? That could be, for example, in this case, we have like a loss of CSF, so that might, hamper the quality of registration because the contrast is different. We know, like, have a gray chord versus dark background. And if you look at this slice, it's a gray chord versus bright CSF. So all those little details will impact the quality of registration. And again, and we have to keep in mind that this is a fairly nice looking image. In general, when we deal with patient data, there could be a lot more artifacts, motion. So that's why the image is sometimes very difficult to rely on. But nevertheless, let's look at our results. I'm gonna do a refresh. So you see we have a big problem here. We have like the spinal cord basically is way bigger than what it should be, right? But that's also because I went with the default parameter, and the default parameter are crap for this particular example. We could use manual steps, like manual params, but slightly different than the one that I used here. And I invite you to play with this, like to basically use the image here. And
what would be the result if you use image seg, for example, IM seg?
For example, if we don't use that,
instead of using the type segmentation, if you use type IM seg.
So IM seg will only works for a particular algorithm. So if, register multimodal. So label, so type here. So type imseg. Imseg will only work for one algorithm, which is this one. And in fact, I realized that this should be better documented. Maybe Sandrine, could you add a note that this should be better documented? But yeah, if you want to use im, for example, we can do something better than what we just did. Right. So let's call it empty im. So in this case, I'm gonna keep this one, but for step 2, we're gonna use im. Okay. And we can use B-spline scene, or maybe let's use scene. Slice-wise 1, iter 3, and we want to use the metric CC. And I think it should give something decent. Let's see. Okay, so refresh. That's the result of our registration. So you see, it's not too bad, but what you observe, like this one here, for example, you see there's like a funky effect of a high degree of freedom deformation. That is due to the fact that the algorithm is attracted to this contrast here, right? So there is a bright tissue, very dark tissue, and the algorithm thinks that that's the edge that the chord should be attracted to, right? So there's another problem here, right? So again, all those little problems. Think about managing a database of like hundreds and hundreds of images and doing a QC on 100 slices per subject and looking for those little details. That's a nightmare, right? So you really want to make sure that you put all the chances for the highest possible robustness on your end before running, when choosing the parameters for your analysis pipeline. So that's why I typically like to rely on the segmentation, because I only have to QC the segmentation. And when I see the segmentation is okay, then I can trust that the registration in 99% of the case will also be okay. All right, so as we mentioned before, we can also register the PAM50 template directly to a metric image, right? So if you don't have any anatomical image, you can still do that. You can basically create a label in the spinal cord in the middle of the FOV, which is what the -1 means. And the label would have the value 4 if the FOV is centered at C3, C4. So that's something you need to adjust depending on your case. Before we were talking about lumbar images, right? So if you know that your FOV is centered at L2 disc, then you would update the label value that corresponds to L2, L3. Run this, and then you can use that created label with register to template, right? And then the PAM50 would be registered directly to your metric image without going through an anatomical T2 image or T1 image. Okay. So once you have registered your PAM50 template to your metric, in our case, the MT data, we can then warp it using the generated warping field, template to MT. So that's what we're going to do now. Sct warp template. Destination is the MT image. Warping field is the warp to template MT. This time I want the white matter atlas because I'm going to use it to quantify MTR within white matter tracks. And the QC report is going to be this one. QC single, here we go. That's going to take about a minute. Good time for questions. I lost the chat window from questions.
Julian, I just have a question regarding different versions of the Spinal Cord Toolbox. I actually have a fairly old version that I'm using right now because I have a paper that's in progress, so I don't want to, upgrade to 5.4 yet. I have several versions in different subdirectories, and I have like a hyperlink which points to whichever one I want to use for a particular day. Are there any other issues regarding like libraries that I should be aware of? Is each version like self-contained within each folder? There should be like no touching.
That is the beauty of this. It's completely self-contained because each SCT folder has its own virtual environment. And actually, I can show you. I'm gonna open a new terminal. If I go to CD code, SCT, this is where my SCT is installed.
Mm-hmm.
I do an ls. When you install SCT, there is this folder that is created. It's called Python. And this Python has the virtual environment. So every Python dependencies are installed in there. And if you have another folder called SCT_5.4, then everything will be self-contained here. However, if you want to activate a particular SCT, then you need to update your bash your bash profile. Right. Just one here, bash rc. There we go. Yeah, so you want to just comment, like you will end up having like different lines like this, and you basically want to activate, like uncomment the path, the SCT that you want to use.
Okay. Okay, thank you. Yeah, what I do is I actually, in that line, I have the link to the hyperlink. So I never have to update that. I just change the hyperlink in the morning if I want to work on an old project and then change it back.
I see. Right. Yeah.
Good. Thank you. I just want to say this is beautiful. This is one of the things that, we know we're going to be struggling with Neptune in the future because of the dependencies. So if we could go back in time a decade, maybe we would rewrite it in Python, but
never too late. And maybe in 10 years from now, we'll regret we haven't chosen Julia, for example.
Exactly. I mean, I've been around long enough to know that, the optimal programming language seems to change every decade. First it was C++, then it was Java, then people talked about Julia and MATLAB, and now it's Python. So we'll see what it is in 2030.
All right, so we have now our empty scan, which looks like this, with the PAM50 registered to it. I change the contrast, we don't see very well. Okay. And the white matter registered to it as well. So this looks like, very good registration, quite reliable, because then we're gonna extract metric within the white matter that is provided by this probabilistic atlas. Okay. We can also look at this in the QC report. There you go. The nice thing here is that on this scan, we actually see the gray matter. So you can better assess the quality of registration while while visualizing also the particular gray matter in this participant. The fact that even though we did not take into account the gray matter for the registration, it still looks okay because the variability of gray matter shape and size across participant is not crazy, right? There is a variability, but it's still within a reasonable range that makes it usable without segmenting the gray matter. Okay. So next thing we want to do is create quantitative metrics. So far, we've only registered the PAM50 to the MT1, but we can't do anything with the MT1. We want to create an MTR, magnetization transfer ratio value, And to do that, we first need to register the MT0 and MT1 scan, or MT off and MT on, as some people call it. So we're going to do that with register multimodal. Sct register multimodal. The moving image, the input image will be the MT0. The destination image will be the MT1. We don't need the segmentation for this registration because it's very robust. We're co-registering two images that are already very close to each other. Okay. The reason I'm inputting the segmentation here is just for the QC report, so that the little panels will be centered in the spinal cord. We're going to use the mask that we created before, and that will help with the robustness of the segment of the registration. And we're going to set up our parameters with only one step, using the image, because it's, again, as I said, it's quite robust. It's the same sequence. The only difference is the empty pulse that is on or off. And we're going to use the algorithm slice-reg, which is a translation, an in-plane translation, slice-wise, but regularized across the inferior superior direction. Metric is CC. I really like the CC one. It's very robust. That's the interpolation after you've done your registration, and QC report. There we go. Okay. What did I do? It's not spine. I guess I've seen too many spine lately. Okay, so let's look at the results. So I'm gonna also load the MT0 that has not been registered. Okay, so that's the original MT0, and then we can compare it with the MT1. I'll change the contrast a little bit. Okay. So you see that it's actually not too bad. It's really not too bad. And now this is the registered one. Right? So what's interesting to do is to compare the registered and the non-registered. I suggest to use the same image scale. Okay. Oops, it's a bit too much. Okay. Now if we toggle between the two, we see that there is a slight difference, right? Especially towards the so here, for example, right? Now we can assess the quality of registration between this one, which looks very good, and this one. It's really hard to say. Really hard to say. Yeah. Anyway, so in this case, those were already pretty close together. In some other cases, it's not like that. So, but yeah, this procedure should give you a fairly robust way to register the MT on and MT off. So once you've done that, you can then compute the magnetization transfer ratio. And you can do that using the function sct compute MTR. The MT0 will be the registered scan, okay? And the MT1 will be the one the native one. Okay, and after we do this, we can finally do our atlas-based analysis. But before doing our atlas-based analysis, I want to say a few words about the gray matter segmentation and how we can account for gray matter segmentation for the registration. I see, Jan, that you have a question. If the subject moved in the superior inferior direction between MT0 and MT1, the algorithm would indeed be different. But that's a bit of it's a tricky problem, because if you acquire images with very thick slices, you know, like here we acquired with 5 millimeters thickness, if you use an algorithm that will allow your images to be translated in the superior inferior direction, you will also introduce a lot of interpolation errors, like a lot, right? And especially if the chord is not perfectly orthogonal to the slices. It's almost equivalent like averaging your slices along the superior inferior direction. So you need to be very careful with that. In some cases, having slight superior inferior motion that is not accounted for could be better than trying to correct for this superior inferior motion.
Okay, so it's better to discard this subject than to try to correct.
Discarding the subject is also a bit severe, I would say. That could be useful, relevant information. So I would say it's a case by case decision.
Okay, great, thanks.
Lisa, I see that you have a question.
Yeah, so the SCT_compute_MTR or MTSAT, I can use that for brain scans as well, right? And if so, is there anything that I need to keep in mind if I were to use those for the brain?
Nope. This one, it really takes 2 images and computes a ratio. All it does. Yeah.
Okay, cool. Thanks.
All right. So let's talk about gray matter segmentation. So we've had some different algorithms for segmenting the gray matter. It started with segment gray matter, which was developed by Sarah Dupont, based on a method that was developed by the Bennett-Landman group at Vanderbilt. This method is no longer available because it was outperformed by a deep learning based approach, which is now called SCT DeepSeg GM. So this one, our experience is that it's really much more robust, and so we decided to deprecate the previous version. So let's try this together. We're first gonna go to the T2 star weighted data. So I'm gonna do cd ... s. Then we're gonna run the function deepseg gm. Input will be my T2 star data, and then I'm also gonna generate a QC. And after I segment the gray matter, what I'm gonna do is segment the spinal cord as well, and then subtract the gray matter segmentation from the chord segmentation in order to obtain the white matter segmentation. Okay? And we're going to use this white matter segmentation to improve the registration to the template, because it will now take into account the shape of the gray matter inside the chord. Okay? So let's look at so I'm going to run this command, and then we're going to look at the QC report. That's my QC report. It now has 2 additional lines, one for deep seg, which is it shows the segmentation of the gray matter on my image. And the next one is the spinal cord segmentation. Okay. So again, you see that the edge slices are not well segmented, but in this case, we don't really care about this because we're only going to compute the metrics within the middle slices, and we're going to avoid the edge slices. Okay. Wow, Rob, this is very calming, what I'm saying here.
She wanted to learn about the spinal cord toolbox. This is Spice.
Hello, Spice.
She's excited about version 5.4.
Yes, Pedro?
So one thing I might miss in the explanations related to how you, pre-processing you do to the images. Are these images at some point corrected for bias field, like low frequency intensity, which I presume it's something you need to do in order to perform the segmentation?
Right. So so I didn't really go into the details of the segmentational algorithms, but it's using some normalization of the batch. So the first step is to extract on a slice by slice basis a patch around the spinal cord center line, and this patch is then normalized, like intensity normalized, histogram normalized, and this helps with these bias that you're describing, which usually run like in the superinfrared direction. But in this case, we do a slice-wise normalization of histogram. So that's our way to mitigate this problem.
Great, thank you.
So, right, so we now have access to the gray matter and the white matter segmentations, okay? And we could use that to compute cross-sectional area of these structures, okay? So we can do that with process segmentation. So I'm going to copy, paste this command here. And we do the same for the white matter as well. Now if we open, for example, this file, it's going to show the cross-sectional area of the gray matter across the different slices. Okay. So you might have noticed that I used a particular flag here called angle core 0. So I told you before that the way we compute cross-sectional area is by computing the angle between the spinal cord center line and the slice. And then we correct for the cosine of this angle. In some cases, we might want to avoid doing that at the risk of, because the risk of doing that is if the angle between the chord and the center line, between the center line and the slice is not properly estimated. Because if it's not properly estimated, then we might introduce a bias instead of reducing one. Right? So in the case where the slices were acquired quasi-orthogonally to the chord, we know that the cross-sectional area is trustable in terms of the angle between the chord and the slice, and so we might want to prefer turning off the angle correction rather than having one that might produce biased or unreliable results. So again, it's a personal choice. I put it there so that you're aware that this flag exists. And it depends, as always, on the quality of the data, on the slice thickness, number of slices, angulation between the chord and the slabs. So yeah, there is a lot of parameters that come into the decision to use or not this angle correction. Again, if you want to discuss this, feel free to reach out to us, post something on the forum.
Julian, just to note that the next break is in within the next 5 minutes or so. All right. Okay. So I think I'd like to finish the atlas-based analysis, and then we can take a break. So now that we've computed the white and the gray matter mask, we can also extract signal intensity in the gray matter. So for the interest of time, we're not going to do it now, but you can run these commands. And what is done here is that you can input with the -f, or actually, no, let's do this. Let's do this. So SCT extract metric is a new command that we have not seen so far. That enables you to extract signal from your input image. Okay. So in this case, my input image will be the T2 star data. And the mask I'm going to use to extract the signal will be T2S_GMSEG. So it's going to be my gray matter segmentation. Okay. I'm going to use this. I'll explain later what it does. And I want to compute this between slice number 2 and slice number 12. The output will be T2S value CSV. There you go. This is my average signal intensity in the gray matter, 1495. Okay. And we can do this also for the white matter. If I then run the same command with the white matter mask instead, and if I do append 1, it will append the result in the next row of the same CSV file. So I can open it, and I have 2 lines now, 2 rows. The first row corresponds to the gray matter label, and the second one corresponds to the white matter label. Okay, and the value in the gray matter is 1495. In the white matter, it's a bit less, 1313. Okay. So we said that we wanted to segment the gray matter in order to have a better registration of the PAM50 templates, and we wanted to account for the gray matter shape. So how do we do that? We do that by adding a step in the registration algorithm by having taking into account the white matter mask and create warping fields out of that. We're going to see how we do this. We're going to use this very long syntax, which I'm going to copy from the script. It's actually here. Registered, yeah, that's the one. I'm copying this one and pasting it. So what, oops. Oh yeah, I need to go into the, right, I need to go into the proper folder.
21. I see. Oh, okay. I did not. I guess I did not copy it properly. I know that's not the right one. It's this one. Sorry about that. So what we're doing here is that we're registering the PAM50 T2 star template to our T2 star data by taking into account an initial warping field that is coming from the T2 to PAM50 registration. Okay. And what's illustrated in this image here is that when we don't do this, the PAM50 that is not accounting for the gray matter shape will look slightly different than the one where the white matter mask is used. Okay. So if your question is, how much does that matter? My answer would be, it doesn't matter very much. When we've done some comparisons with and without this gray matter shape informed registration, and quantitative results were quite similar. Another thing I want to add is that every time you do a registration, there are risks of doing some registration errors. So down the line, my approach is to not necessarily account for this gray matter shape unless you're dealing with particular conditions where the gray matter is drastically different from the average gray matter in adult individuals. So now we warp the template. Any questions so far? So after we've registered the PAM50 T2 star on our T2 star data, we can then do the same and register the template to the MT data via the T2 star to PAM50 registration. Okay. In that case, we will use as an initial warping field the one that we've just calculated. Okay. Again, this is an optional step. You don't need to do that, and we will slightly modify your results. In some cases, it might make them worse. So, take this with a grain of salt. But I just wanted to make you aware that this is a possibility. And in fact, as we are, going with images of higher and higher resolution from 70 data, maybe this will become the a go-to step when we want a very precise registration. So I'm going to the MT folder, and now I'm going to run this this command, which is the same as this one. And after we do this, I'm going to warp the template to my MT1 data. Any question? I know these last steps might have been a bit confusing for some of you.
One question in the chat from Catherine.
Mm-hmm.
If you have bad data, would it be obvious by this step? At what stage do you typically weed out bad scans?
Right. Right. So first of all, the bad data could be the bad data, could be like a bad anatomical data or a bad metric data or a bad T2 star weighted data. So, you know, if, for example, in this example, if I had bad T2 star weighted data, which is often the case because it's difficult to get good T2 star weighted data with a nice gray matter butterfly, I would typically avoid this step. And it's usually the reason why I want to avoid this step, because I see many people, you know, blindly like using this step, and when we look at the data, they are actually, you know, awful, and the gray matter segmentation is bad. So that step would actually make the registration worse. So, you know, you would know if you have bad data by looking at your data. You know, if you realize that there's, you know, a lot of motion, or if the chord is difficult to distinguish, if there's some like ghosting, then that will tell you whether some of the steps are, you know, are working or not. And again, looking at the QC results will also tell you if the data are of decent quality or not. You know, for example, these slices here, I can tell right away that they are good. But if all your data look like, you know, these ones here, these last slices, then there's a problem.
Wonderful, thank you.
You're welcome. Okay, so we've just finished this step. So we can look at the result of the gray matter based registration, and, you know, like before, the registration is good. The gray matter shape is slightly different, and it looks closer to the gray matter of that particular individual. But again, down the line, it will not make a big difference. That's the take-home message I want to give. Any question before we do another break?
Yeah, I have a quick question about the QC results on the last two lines. So if I toggle the overview on the Palm 50 register, I see some dots on the first and the last slide. There seems to be some data missing. I don't know what that's about.
You're looking at the QC.
Yeah.
Here, for example?
No, I think you might need to refresh for the last two that we run.
Oh, yeah.
So the next to last.
Right, yeah, excellent. So why is that happening?
Yeah, so on the wrap to template, the overlay skips the first and the last slide. And then the next to last one, so on one up, that one, there's some, if you do the overlay, there's some dots on the last.
Okay, yeah. So, okay. That is a great observation. This is related to the fact that, so these are edge problems. We are basically deforming the warping fields at the edge of a slice, and which is due to the fact that the segmentation is not existing at this slice, okay? So there's no segmentation there and no segmentation there. So if you want to estimate a warping field that is based on the segmentation, then the warping field will only start at this slice, right? But the thing of a warping field is that it's defined in the space of the destination image. So if we represent the warping field, and if we apply the warping field to an input image, in this case, the PAM50 template, then in some voxels of the slice, there is no warping field. It's not defined, which is why the voxels are 0. Yeah, so these are edge cases. And maybe, Sandrine, can you add a note that we should probably like explain this or like, yeah, make a mention of that, because yeah, it's a good point. Yeah, it's a good point.
And I guess that's the same explanation then for the last one, right? Wrapping to the template.
Yeah, exactly.
Exactly. Okay.
Exactly. Yep. In fact, you could compare the two approaches with the QC reports. Right? Okay. And quite frankly, I find that the previous one was already working pretty well. Yes, Sandrine, you might also want to add a note on the fact that we need to mention the fact that there is much less slices on the gray matter based registration because the coverage is not the same between the gray matter and the empty scans. That's also introducing a lot of confusion. Yeah. Good. I think this is a good time for a break. And should we? What's the